Welcome, everybody. This is the lecture video for Unit 7 covering the NLP data pipeline. And as usual, all of our materials here are based upon Intel Corp's internal training materials, AI for Workforce. Last week and the week before, we were looking at document similarity and how we can identify when things are similar or dissimilar to kind of try to extract meaning from them. We also looked at converting text into vectors, simplifying those vectors to try to get metrics for how similar text is. And then we looked at word embeddings and how to measure document similarity with those tools. This week, our agenda is as follows. We're going to look at this concept of data pipelining, how it applies to exploratory data analysis, how we are now going to start to use some of the data that we've been aggregating and generating and all that to train and test data sets to figure out if our models are good. And then we'll look at advancements and limitations of LLMs and what exactly LLMOps is. Right. The focus this week, of course, is looking at building our own models and creating a data pipeline, but we have to figure out what that word means first. And so let's say we use this analogy of a factory where they build automobiles, right? So there's a production line, and for anybody who's ever been in a factory environment, usually a production line is kind of a sequential series of steps that builds a car. For example, like one station might put in the engine, and then they might apply some body parts, and then they'll throw the wheels on, and they'll, whatever the steps are. And the important aspect of it is really that it's a linear process, that it goes one step to the next. All right, so once we get like what a pipeline is in terms of like maybe a real world example, we also kind of have the same sort of a process that happens when we work with data. So data sometimes when it's generated or gathered from real world sources has to be processed in a number of different ways. Maybe there's some data we remove. Maybe there's some data that we transform or do math with, or there's data that might be missing, or the data maybe is somehow corrupted, right? Or whatever the operations are with the data, those are done sequentially, right? So for example, I wouldn't, clean the data and do math on it afterwards, right? Necessarily, would I do the math first, or would I do the data cleaning first, or would I put it into a different file format? Or you feel where I'm going with this, right? You wouldn't do multiple tasks at the same time. Like a production line, you would handle one task at a time in a fashion that makes sense. And it might be, some of the early steps might be just like, well, that record's no good, or we don't need these columns, for example. Cleaning data is always a big issue. And, one of the nice things about using publicly available data sets is hopefully they've done some of this, right? There are examples of data sets out there too where they don't pre-clean them. And one of the tasks, and we do that in our data analytics class, is we get people like the liquor store data from, I forget what state it was, and it has bad data in it, right? Or missing information. And then what do you do with the data after you process it? Well, you store it back in a text file, and then you might process it again, right? And so that's part of the pipeline of working with information. The algorithms that we'll use with NLP, right, will focus on text, right? So like having a way to process the text in a meaningful way becomes important, right? And look at bullet number 3 here, and I think this is one of those pervasive things in IT, especially when you learn to like deal with problems, right? Whether you're processing data or you're writing computer code or both, right? Is to take a problem that's huge and just focus on one little aspect at a time. Maybe for this step, I'm just getting rid of the columns that we don't need. Or maybe my step is to take all these word vectors and reduce their dimensionality, so I have less to process. But whatever the task is, you're doing one small task at a time. And I think that's really exemplified pretty well when you write like Python code in a notebook format is you're not like worried about like running the whole notebook. You're dealing with little pieces, moving along. Um, when you start to look at like the typical tasks, right, in NLP, there's text pre-processing. That's kind of what we were focusing on last week. And then we start to look at exploratory data analysis. For example, we visualize things. What does it look like? Do we see trends, anomalies? Then we model our data, meaning we do training and testing, and then we deploy the working application that's utilizing that tool. And if you wish, and I'm going to expand this graphic just a little bit here, is notice like one pipeline that we might use for NLP. We might take a text document and break the sentences apart. Then we'll break it into words with tokenization. Then we start to tag parts of speech. This is a preposition. This is a noun. This is a verb. This is, proper noun, whatever. Then we do stemming and lemmatization, where we get to the root word, right, and the correct meaning of the root word. Then we eliminate stop words. Then we might do some parsing on depending on dependency, like what words we need to focus on. We need to focus on things that say, I don't know, nuclear, for example, or we're looking for noun phrases or trigrams or bigrams or whatever, right? And then we're looking for certain information. And as we go through that pipeline of processing the text, and it's all separate steps, then we end up with parsed text that we can use for other tasks. So here they start talking about what does a typical NLP pipeline look like. Now, some of this we've begun already, the text pre-processing, we've gone through that process. And now we're also kind of looking at like the exploratory data analysis. That's often the visualization piece. Then we transform our data, right, which we've been going through as well. Then we start doing some modeling, predictions, and then ultimately deployment. When we look at the text pre-processing, the one really good example is how we vectorize words or sentences. And this is often put into a multi-dimensional space. So like the pre-processing part of this, which is to maybe reduce the number of vectors that we're processing, makes it easier to do the processing. So that's one aspect of it. Once again, some of the steps we learned in recent weeks was tokenizing things, splitting apart the words or the sentences, flipping everything to lowercase, removing stop words, stemming, and lemmatization. We'll look at each one of these separately really quick. So tokens are the building blocks of natural language, right? So for example, a sentence can be a token if it's part of a large document, and then a word can be a token within a sentence. So we can tokenize sentences and we can tokenize individual words. So for example, just do it can be broken down into 3 tokens that we can deal with separately. When we start to work with Python, I mean, that's exactly what we're seeing here. Is where we take like a whole sentence like we see here, right? And we can run the NLTK library on it where they have a tokenizer, right? And we're just basically taking that sentence and breaking it into its individual words and putting it into a data structure. The one thing I do tell my Python students is like, we don't necessarily have to do that with a fancy library like NLTK, because if you think back to like basic Python class, we learned how to process text files that way without external libraries. Right, you can split a sentence, you can drop it into a list, then I can read through the list and analyze each word, each letter when it comes down to it. What is nice about using a library though is you just ask it to do it. You don't have to engineer the process of it. It just does it, right? So that's why we use the library. It just speeds up the work. The previous example was tokenizing words. This one's tokenizing sentences. So we start with 2 sentences, then we break them apart into 2 sentences inside of a Python list once again. Another approach is to take all the words that are coming in and lowercase them, right? So in other words, you get a word coming in that starts with like a capital letter. Is that a different word than one with a lowercase letter? Well, numerically it is, right? Because a capital B and a lowercase b have different values. So very common to take language and switch it to one case or the other so you have that much less. You have half as much to process in some circumstances, right? So that's a technique. And you don't need any special libraries for that. Python just does that, by the way. We also do stop word removal. We've been talking about this for a while. So those common low-level words like for or the or in or and or those kind of things. They appear frequently and often don't have any meaning that changes any of the language, right? So NLTK does have libraries for doing that too, right? And you basically just take your text, run it through the stop word removal, and remove it basically, and then you have like the filtered or leftover words to deal with. And it says the command stop words dot word English selects all the stop words from English which can be filtered away. Right? And you know what? Stop words can be focused on other languages too. They have them for other languages, by the way. And then there's also different levels of them, right? So if you look at like this is all like pronouns on this page, right? What this one does is it actually shows what some of the stop words are. Then there's the concept of stemming. We'll also look at lemmatization, which are kind of related. But stemming is basically where you have a collection of words like the ones you see on the left here that really kind of all have the same root word, which is to consult, right? And that becomes, the root word, whether or not that's accurate or not, right? And I'll have you consider maybe the word consultant is a little bit different than the word consult, but certainly they all have the same root word. So if we were to run the NLTK stemmer on the sentence running, singing, and learning, we might end up with run, sing, learn. And you know what? That is basically the same, right? I mean, it is really kind of putting together the same concept in a little bit more efficient way. Now, lemmatization is a little bit different in that it does the same thing. So, for example, it gets you down to the root word, but studies might be stemmed to study with an I, but that would be the stemming approach. But the lemmed approach would be to get study, which is different than study with an I, right? Therefore, it does require deeper knowledge of the language, right? So it takes more processing, takes more code to develop these tools. And there are these free tools out here. You can go explore that one if you wish. But a really good example of it would be here. Like, for example, if I stem the word caring, the stemmer might realize, I just get rid of the ing and then I end up with car. That does not mean the same as caring, right? Lemmatization would understand that the root word of this really is care, and that has a significantly different meaning than the word car, right? So that's kind of the advantage of it, but it does take more to process, so more computationally expensive is the way to say it. As we move through the NLP pipeline, we get to the exploratory data analysis, and probably the most common way to do this is just simply to visualize the data statistically using tools like Tableau or Excel or Python, right, with the visualization libraries that it has. So EDA, when I say that, refers to exploratory data analysis, right? We see some like a little snapshot here of some common visualizations. The reason we do this, of course, is to discover patterns, to see data that is anomalous, or to check our assumptions, where I can just look at a data set and I thought it would be here. Oh, no, I guess it's over there, right? That type of thing. And typically this is a visual representation. And once again, when you're dealing with multidimensional data, it becomes really important to reduce that dimensionality to make that happen. Here they link us up to a Kaggle data set, which are consumer reviews of Amazon products. And if you explore that list, it's, I guess, 34,000 consumer reviews for things like the Kindle and the Fire Stick and other Amazon products, probably like the Amazon Echo, for example. The data set includes basic product info, rating, review text, and more for each product. We could do a little exploratory data analysis on this and see what kind of insights that we can gather. But first, you got to kind of look at the data. So if you go over to Kaggle and explore it a little bit, you'll see information that kind of looks like this, right? And you'll see they have like name, reviews, the text of the reviews, whether it's recommended or whether the review was helpful, the data, the verb or the words in the review cleaned, right? So I don't know if that removes stop words. It doesn't seem to, but all lowercase or whatever. And then lemmatized, basically getting to the root words where they boil it down. And notice how there's no stop words in there, and they're all lowercase, and there's certain words that are pretty rooty, basically. And then we have a polarity, which means how much of a difference is there between, I believe, positive and negative reviews. Is there a lot of positive and a lot of negatives, or is it mostly positive, or is it mostly negative, right? And the higher that number, the more disagreement there is on the product. Okay, so the first step is basically to see like what words are common in the reviews. And once again, they point us back to word clouds, right? So like how often words appear in these reviews. And right, we know this already. The bigger they are in the word cloud, the more they've been used. So for example, if you look at a word cloud for the Fire HD8 tablet, right? All right, so a lot of people use the word tablet in the review, or love, or great. So, I mean, those are really big. Love, use, tablet, right? Price, that doesn't indicate positive or negative price, right? Easy, Kindle, good, buy, whatever, right? I don't see any words that are really large that are negative. I don't know. And I'm trying to even look at the small words, and I'm not really finding like a lot of words that are negative. Here's one for the Amazon Fire TV thing. Once again, look at what words are big. So Echo and Alexa, that must be integrated into that product, I would assume. And a lot of people are seemingly loving, and music is good, for example. And the same thing with the Kindle, right? I don't see a lot of negativity here. So I feel like a generally positive vibe from all that, right? And they're pointing that out. So we saw that love, use, buy, great, easy are some of the more frequently occurring terms for almost every product. That gives us an insight into what people think about them, right? Is this really a very scientific tool? That's arguable, but it does give you a sentiment quickly by looking at it. So if we did like a deeper analysis, like what we could do to improve products, right? They would start to analyze some of the sentiments for each product and whether it's really positive or negative or opinionated, and try to figure that stuff out. And you'll notice here that those are, usually analyzed the polarity data that I was talking about before, and how the Echo in white, I guess, had a pretty high polarity number compared to some of the others, right? And I think these numbers are all pretty low, really. This is like, I think in the 30% range. So in other words, there's not, I'm guessing, right, most of the reviews are positive just because of that number not being super high. When you do look at the percentage of reviewers that recommended a product, and that is like way up there in the upper 90s, right? So people are recommending these products. So they're getting a high rate of recommendation by the people that reviewed them. So we can use then, exploratory data analysis for word count, sentence length, stop words, and trigrams. And so, for example, we can use as a example data set here the Million News headlines, right? So they had this aggregated data set of just news headlines over a number of years. You can find that data set out there if you wish. But as they analyzed it, they figured out some things, right? It says, looking at the number of characters present in each sentence, so individual letters and stuff. They range anywhere from 10 characters up to 70, and usually between 25 to 55 characters, right? So it looks like they kind of try to cap it off at 50 characters, and it's probably like how much space you have to print with or put on the screen, something like that. Then they look at the number of words in a headline, and it averages or ranges from 2 to 12, but mostly falls between 5 to 7 words. So pretty concise, right? When you look at the word length analysis, most of the words have typically like 3 to 9 letters, with 5 being the average length of the word. So really short words and headlines. Also interesting, right? Stop words apparently dominate headlines. Like, for example, to, in, for, of, on, over, etc. Those are very commonly found in headlines. Very, very commonly. When you start to look at words other than stop words, and I think this is kind of an interesting graphic. So over 15 years, and this data set was published in 2021, so stretching back to like 2006, basically, the like non-stop words that dominated the headlines. And you can look at US, Iraq, war, police, government, man, etc. Right. And that makes sense, right? Because those are like what kind of words you see. Like if there's a conflict happening, yeah, you're going to see the country names up there a lot, right? Like if they were analyzing today's news, they'd get a lot of like Gaza, Palestine, Israel, Trump, war, Hamas, that kind of stuff would be real prominent for sure. When they start to look at trigrams, like groupings of words like two-faced court and anti-war protesters, they have a collection of those. And if they're doing trigrams, they probably have other large collections of words that they're looking for that appear frequently as well. The sentiments tend to be generally pretty neutral. So in other words, the headlines are written in a way that tend to lean towards neutral. Although if you look at the chart, and I'm not sure how exactly they're plotting this, but it looks like it's not, most of the data points, I mean, they're shooting for neutral, but they're not exactly in the middle, right? It's a little leaning to one side more so than the other. So this is like one of these things that they actually try to measure numerically, which I think is pretty fascinating. All right, as we kind of move through the pipeline here and we go through the data transformation part of it, and this is stuff that we've been working on once again in the last few weeks. We started with bag of words, right? Where you just take a bunch of words and you throw them into a data structure and you start counting them, like how many times they appear. So this is one way to take words and kind of apply numerical value. Like how often does it happen? It's a very primitive, but important technique. The other approach, of course, is the TF-IDF thing, which combines kind of like the frequency with the inverse document frequency. So the less a word appears, the more important it might be, which gives it more meaning. And basically tells us we shouldn't ignore that word, right? If the happens 500 times and war happens once, war might be an important word, right? Then we also have the word embeddings, or basically where we're taking words to vectors, right? And trying to put them into different meaning based on context. And therefore, is probably considered a little bit better than like TF, IDF, and bag of words, basically because of the context aspect of it. So like they're given meaning by how they're utilized, right? Those are things that we looked at recently, so I'm going through them quickly because I think we've already hit those topics pretty strongly. As we kind of move through the pipeline here, what comes up next is the modeling, right? And they're having us do a look back here because this is kind of like where the new stuff starts to kick in. Generally, what we've done so far is when we're working with text, right, we import the required packages and libraries, we bring in the data set, we process the data set, and then we create some sort of a model or structure that then we visualize or whatever. Now we're at the point where we can think about building models with this stuff, right? Because, if we have done the pre-processing and we're moving it through the pipeline, modeling comes next, right? And if you remember, the whole point of modeling is to build a model, train it, and then have some data to test it with to make sure that it's working correctly. So one of the big things that we have to do is come up with a technique for basically taking the data that we have, and setting it up so that we can train and so that we can test that machine learning algorithm. Machine learning algorithms, if you remember, are typically used for classification or regression, and that applies to supervised learning algorithms. And that usually means we take our data set and split it in two, right? And these are things that we have learned before, by the way. The first set of data, usually the testing data, the training data, I apologize, is usually the propensity of the information we're feeding in, larger amounts of training material as opposed to testing. The second collection of data, of course, is used to test what we have just modeled to make sure that things are performing as expected and we're getting the expected values out of it in the process. All right, so I think that we've talked about that certainly more, enough, right? And we have used the scikit-learn libraries to do that training, testing, data split. Real common ratios are like 70%, 30% for doing that. So 70% train, 30% test. You can see here from the Python code, they're splitting it 2/3, 1/3, 2/3, right? So the test size is 1/3, implying that the training size is 2/3 of the data. All right. So now that we kind of have figured out this data pipeline thing and how we kind of do the testing and training of the models, now we're getting ready to the point where we can start to use these things to build something. But we do have to look at some of the advancements and limitations of large language models to understand like how we move forward from this point. So you have to start to think about what is the need that you have for applying the language model to some sort of a application-driven solution, right? Like, and what limitations or advancements are out there that might help us to do this. So as we kind of go through this, these are kind of the steps for figuring out your scenario. First, we define our use case. So what is the task that you're going to apply this to? You know, are you going to use it as a chat bot to help your customers? Are you going to use it to help you write code? You know, what's the use case? There are models out there, proprietary ones typically that are pre-trained, but there are open source ones that are too. And those are trained sometimes for years on really large data sets. And they give the examples of the GPT-3 or BERT. And you can take those models and then start fine-tuning them to your information and scenario. We also have to look at the model architecture, you know, so there's different advantages and limitations of different LLM approaches. You know, so for example, there's recurrent neural networks, right, where the data backfeeds through the network. There's transformer models, and there's also the generative adversarial networks where an LLM generates information and then it tests that information that it generated to see if it can detect that if it's fake or not, right, to try to make it better. Remember all that? Then we look at our data set compatibility. Is the data that we're feeding in going to be compatible with the thing that we're trying to generate? So, you know, how much data are we feeding in? Is it focusing, for example, on one language or multiple languages, or is it coding language, right? That's a language also. And is it specific to the kind of thing that you're trying to do? So not all language models work well with all kinds of information or tasks, right? So some are specialized. You know, and computational resources, assess the computational requirements. So, you know, depending on the kind of thing that we're going to do, there's going to be different demands on the technology. How much memory do we need to run this? How many CPUs do we need? How long does it take to train this model? And if you have language models that have extensive parameters, that can be, as they say here, substantially computationally expensive, right? Whether you own the gear or you're renting space in the cloud to do it. We also have to evaluate the performance of the models, like how are they working? Are they accurate? Are they doing what they're supposed to do? And do they work well with your specific use case, right? They may or may not. There's a bunch of things that have been happening in this space, obviously. Like there's been huge advancements in language models. BERT and GPT are like the two big ones. And they were very, very significant when they were released back in the late 20 teens. Don't quote me on dates here, like 2018, 2017, 2019, things were really happening there. And they use basically what we call the transformer model to do this work, right? And you can look at this graphic here. Once again, I'll make it a little bigger so we can look at it, where you get inputs, they're encoded, they're decoded, and then they look at different types of output probabilities or possibilities based upon how that it's all put together. But some of it is based on context, some of it is just more training. Some of the training is deeper. There's different types of training, et cetera. But the transformers are really big for BERT and GPT. We also have these multimodal LLMs that have been coming out and a lot of the big popular ones are doing this now, right? So I can go to like Chat GPT or maybe Copilot's a better example, and ask it to generate a graphic. So they've integrated that capability into it. So they can handle helping you write your paper, making a deep fake image, creating a phony video, and writing your computer code. You can do all those things. There's models like VisionBERT and VilBERT that are used to kind of combine multimodal AIs, right? One real common trend in the past is like if you wanted to generate an image, you go to an image one. If you wanted to go to a coding one, you go to a coding one. And that's obviously become a lot more multimodal lately. The other thing that I think is really important too is this cross-modal concept where we can have an image data set. Like think back to the examples we've used in class, like that's a dog, that's a cat, that's an orange, that's a banana, that kind of thing. And then you take words and attribute the words to the images as well, right? Giving it like kind of like a double meaning, right? And that is really a big movement too. So clip and align, leverage training on those different modalities. So the aim of those tools is basically to combine modalities. We also have this masked language modeling for pre-training methods and next sentence prediction. And these are things that we see in action, especially like next sentence prediction is a thing that I've seen a lot in like my email or my document creation. Also my coding engines, right? Like I type a line of code and all of a sudden it's like giving me the lines of code I would type next because it's just logical that would follow. Either that or it's learned how I do my work and mimics it, right? Like if I type an email and at the end of it, I might, let's say, recommend to a student to reach out for help. I might say, hey, if you have any questions, please email me, that type of thing. And Gmail just puts it up on the screen. I just press tab and I don't have to type it, right? But I would have typed it. So it knows, contextual word embeddings are important too. So they call these like LLMO, right? See that? And so embeddings from large language models and GPT that consider the context of the words and what they mean, and that the words can mean something different and put into different contexts. But it looks at the words around something to get the context, and therefore we get much better results with those types of tools. When we start to compare some of the traditional models to large language models, right? And look at like semantics, for example, bag of words and n-grams. Okay, we can see why those are useful tools, but large language models have contextual understanding, not just like, hey, look, there's these three words together again, Green Bay Packers, that type of thing. Feature engineering. In traditional models, we did this manually. In large language models, it becomes automatic. We tell the models to adjust themselves, right? That's pretty cool. Deep learning. Remember, that's an aspect of machine learning. We don't usually use that in traditional models because of the computational expense of it, but large language models do utilize that, and is one of the reasons why they are able to do things like context transfer learning. Um, the training that goes into a traditional model doesn't necessarily propel itself into a different one, where large language models, because they are like multimodal and cross-modal, they kind of pre-train and fine-tune themselves. The model size is really important here too. And notice with LLMs, they can literally have billions of parameters. And the more parameters that you're throwing around in software, right, the more computational memory and processing and storage you need to make all that happen. But because of that, that's why the large language models are so effective. Traditional models don't use symbols and grounding, but LLMs do benefit from that. It improves their accuracy and performance, and basically allows them to adjust better to different types of scenarios. There are some limitations too that we should talk about, and basically large language models, even though they appear to be knowledgeable, really are just doing an imitation, folks, right? Still. They can imitate language comprehension, but they show that probing shows a basic understanding gap. They're not like people, like when a person gets it, you get it, right? And you can allude to something and a person will still understand. LLMs basically just work with math. So yeah, I mean, I think that's pretty weird, so they're not really getting any meaning. They're just seeing the mathematical correlation, and that's not meaning, folks. They also have difficulty interpreting and explaining output. So in other words, why, and we had this like really interesting presentation at our faculty in service this year, where they asked, the lady asked the AI to generate an image of somebody in a certain, of a certain gender in a certain country, and then painted them or created them as a certain race and wielding a weapon, which was really interesting, showing that the AI had bias. Like, why did it show that person in that race with a weapon and then that person and that without? So there are biases, unfortunately, right? So that it's all about the data that's fed in. But sometimes LLMs create stuff that's not correct, right? And so I've run into this where I ask AI for help to, let's say, generate some content like lecture notes are a good example. And I read through them and go, oh, that's not right, or that's not really what's meant there, and I have to fix it, right? So whenever you use tools like that, you got to be really careful that you're generating stuff that might actually not be right. There's also this aspect that LLMs hallucinate in principle. And notice they say it generates nonsensical, off-topic, or factually inaccurate responses, kind of like what we were just talking about, right? In ways you can tune these, so, and on specific domains. So if you have your own data and you're training that AI on your data, it might minimize the hallucinations, right? But ultimately, you need people to challenge these things. All right. And I think that's pretty interesting. There is some difficulty with ambiguity and contextual understanding, right? People kind of get meaning of other people, even if not all the words are spoken, right? Because we look at a whole bunch of different clues in what they said and how they said it, the inflection of their voice and how loud, what, the tonality of it was, all that kind of stuff. And therefore, they can kind of guess wrong about the context, and there are the biases for sure. All right, so now that we have all these models and considerations and advancements in place, let's look at how we can, deploy this kind of stuff and lead to what we call LLMOps, which is basically sort of an offshoot of DevOps, where you take developed computer application solutions and deploy them operationally into an environment. Now, this is just kind of a term that they've developed to talk about the fact that we're taking large language models now and using them as a back end for other types of software solutions, right? So we're calling it LLMOps, based, of course, on DevOps. Of course, LLM ops is part of machine learning ops because it leans on that, but it's tailored for large language models, right? So there's a collections of tools, platforms, and other operative items that are used to kind of deploy these types of applications. Um, and I think it's kind of interesting when you look at this little life cycle thing here when the GPTs like GPT and BERT were coming out in the late teens. um, it took them a while to train, and as the training got better and the models got more powerful, and then they kept releasing new ones, right? So like Chat GPT 3 came out basically kind of right when the pandemic was hitting full force. And then by late 2022 and early 2023, people started to catch on. Hey, there's this Chat GPT thing. Check it out, right? And the media started getting on it and like started showing the stuff that it can do. And now they're working on GPT 4 and 5, right? And but it take a long time, and this is, I think, kind of interesting. It takes a while for the model to train itself because they're feeding it data up until that point. So like if you use GPT-3, it's kind of stuck with data points that were trained into it in the, mid 2020. The GPT-4 has got 2023 in there, et cetera. And they kind of get, I'm not going to say locked in time, but we look at those models, and the data sets that are provided to them, and those are foundational to those models, but information evolves, and we know how quickly it's generated these days. It's huge. So you select your foundational model, adapt to downstream tasks, evaluate, and then do your deployment. And so let's kind of hit these one at a time. So when you select a foundational model, you can use a couple of different approaches, and this is kind of interesting. You can use proprietary models. I could go to the OpenAI company, the makers of ChatGPT, and pay them money to use their models and their APIs to build things for us or whatever, right? Or we can go to open source models, right? There's a bunch of those out there. They give an example of like Hugging Face, Stable Diffusion, and Bloom. Some of these are, places where we can host models. Some of these are places where we have pre-trained LLM libraries, and the proprietary ones, of course, have pretty extensive training. And you can see the companies that are listed there, right? These are really big AI companies, but the information is proprietary, right? As we start to decide, which types of models are we going to use to build our application, right? And it's really common for a lot of companies to use the APIs of pre-trained models from private companies. Why? Because they're there, right? And they're already pre-trained, and then we just have to tune them to our tasks. Notice that it says LLMs without specific knowledge can hallucinate, right? So it does become important if you're using it for, let's say, an internal enterprise task, that you use internal enterprise data to fine tune and adjust that model. They have examples of tools that they use, to predict things. So in other words, prompt engineering adjusts input to match expectations. So for example, if I'm asking a generative AI engine, which I know struggles with advanced coding, to generate advanced coding output, I might not get what I'm really looking for. If I give a fundamental programming prompt to build like some code structure, knowing that it's really not going to be able to do the super advanced thing, but it can at least give me the structure, I can engineer my prompt accordingly, right? So I'm not going to ask it for the moon. I'm going to ask it for something a little bit more reasonable. They do have, tools out there, LangChain and HoneyHive, which are examples that help to version your prompt template. So in other words, to put you in a format that works well within certain engines, right? One thing that people do share on the internet, and there's a site like Snack Prompt, for example, where people share prompts that they've used that have been successful, and then you can just take those and tweak them a little bit, and then you will get good, successful results too. Where otherwise, like what you do discover is if you ask an AI to build something for you, sometimes you have to ask it, well, that's not what I was thinking. I was thinking more like this, and it really comes down to how you're putting that prompt together. Okay. Adaptation to downstream tasks, basically fine tuning the model as you're kind of going through the process. So like you might do that, um, in terms of like how you are sending in the information. But it also, as you're evaluating the information on the back end. So basically, it says here, it improves your model's task performance. So there's more training involved, but lower inference costs. We don't have to worry about it coming up with stuff that's BS, right? How much information you're feeding into a prompt is often kind of a thing too, right? Do I want to give it pages and pages of info as input and then go, oh, that's not what I want, or maybe that is what you want? So like we try to find efficient ways to put in a prompt and efficient ways to get the output, right? One of the big points they're making here is this: if I can write a prompt that's shortly worded but to the point, it's much more efficient, right? So it's lower input processing and then perhaps lower output processing costs as well. All right. Adaptation to downstream tasks. So we keep going here. External data, and it says foundation models can become outdated soon. And notice here they say ChatGPT-4 was trained on data before September 2021. And they're making also the point that they need external data to avoid hallucinating. And then they have these tools that are coming out now, like Llama, Index, LangChain, and Dust, that chain the LLMs to other agents and external data. So in essence, kind of giving them fresh data to consider, right, as they move forward. So they're giving this example here about embeddings from LLM APIs like movie summaries or product descriptions can be used to develop search, comparison, and recommendation apps. But they have these tools, Pinecone, Weaviate, or Milvus, vector databases that can store embeddings for long-term memory. So in other words, if your Python libraries like NumPy arrays, right, can't hold enough data to do the processing, we have these other tools that can store the information, and they have databases that can store vectors, so that we can process the data later, and it becomes necessary with super large data sets, by the way. Alternative LLMs can be used in AI products in numerous ways: instruction, prompt tweaking, model distillation, etc. So I think what that really is saying to me is to use the large language models to help tweak your prompts, right? Or to make your models better. So you can use the AI to help you with the AI. So ultimately, how do you evaluate whether your language model is working, or are the responses you're getting good or bad? So one way is just to let people do it, right? Human evaluation, or you can write software to do it, or you can actually ask the AI to evaluate yourself. And you think of like generative adversarial networks kind of operate that way. But what I will tell you is the human part of it is really, really important, right? Not that we can analyze everything, but we can also come up with those automated ways. They do have tools like HoneyHive or Human Loop that have emerged that test the quality of LLM responses and benchmark them. And you figure that was only a matter of time before somebody figured that out too. Once we're done evaluating and we're happy with what is happening, we can then put the application out into the wild, as they say, right? We deploy it. And then we have to make sure that people can get to it and use it, whether it's an app form or browser based or whatever. Make sure that it's secure so people can't mess with it. And then we do the typical tasks that we do when we deploy any application, which is we make sure is it working correctly? Are the servers okay? Is the processing okay? Are we utilizing our resources efficiently? And we, do have tools out in those environments too that can monitor applications out in the wild and how they're working. And so that they have tools such as Y Labs and human loops that monitor these LLMs to make sure that they're working okay. Some reflection questions here as we kind of end up. I'll let you just kind of look at those briefly. And then our bibliography here for the materials in the slideshow. And folks, this video ends here.